Let's talk about current and resistance today. We have finished the electrostatics part of the course where we were not allowing charges to flow freely. But now we're going to change things up and allow them to flow. And with that will come the definition of electric current. So let's start with that today. Electric current is important because most practical applications of electricity use moving charges rather than, or a flow of charges rather than stationary charges or static charges. Today we're also going to introduce a circuit element called a resistor. We can talk also about how energy gets transferred in an electric circuit. So, with that, let's define electric current. It's the rate of flow of charge through some region of space in some unit of time. So, the unit of current that we use in SI units is the ampere or the amp, capital A. 1 amp is 1 coulomb per second. And we generally use capital I as a symbol for current. We're going to get in the weeds a little bit on this. And one of the reasons that we do it is not so much for an immediate gratification, but for purposes that we're going to use much later in the course. So I think it might be interesting to sort of take this little detour as we talk about electric current. So the first thing we want to do is, let's assume we have charges moving perpendicular to some surface of area A. And let's say that in some amount of time delta t, we have some amount of charge delta q passing through that area in that time. The average current would be delta q over delta t. The direction of current, by the way, is the direction in which positive charges flow when they're free to do so. That's how we define it. Now, we all know that most of the time that we use devices, they run by means of electrons which are negatively charged. But be that as it may, we're going to use this convention for now because this is the convention that everybody uses. So you can imagine though, if I take the limit as delta t approaches 0, I can get an instantaneous current, just like you would do when you do an instantaneous velocity or an instantaneous acceleration. That instantaneous current, that is just the time derivative of the charge, and so it's dq dt. When I talk about charged particles passing through a surface, they could be positive, they could be negative, but we typically assign the current convention to be in the direction of positive charge flow. And as we said before, most of the time we're talking about electrons, and so they flow in the direction opposite the direction of the current flow that we indicate. Oftentimes we'll call a moving charge a charge carrier. Let's talk about drift speed of current. So charged particles move through let's say we have a cylindrical conductor. We have a cross-sectional area A of the conductor, and suppose we have little n number of charge carriers in that volume. So we have a volume, we have an area A and a length L. We can talk about the fact that we have a number of charge carriers. We can talk about the number of charge carriers we have as number of carriers times the area times the segment length delta x. That would give me the total number of charge carriers in a segment. Now, if they each have a charge little q, then the total charge in that segment would be Na delta x times q. Moreover, suppose that the carriers move with a velocity parallel to the axis of the cylinder such that they experience some displacement in the x direction. And then we call that velocity v sub d. I can write that as v sub d is delta x over delta t. I can therefore write delta x as v times delta t. That would allow me to rewrite my total charge in the following way as Na drift velocity delta t times the charge of one carrier. Moreover, if I divide delta Q by delta T, now I have an expression for the average current in that segment that I can write as the number of carriers times the charge of each carrier times the drift velocity times the area, where V sub D is what we call the drift speed or in some cases drift velocity. Now, as I say, this is going into the weeds a little bit, but we're going to use this later on. So let's talk about the motion of charge carriers in a conductor. So if I apply a potential difference across a conductor, we set up an electric field, and of course, instead of having random motions of charges, now the motion of the electrons isn't going to be random anymore. So we have these zigzag motions until we apply a field. And in that case, when I have a field, the drift velocity or drift speed is going to be relatively small compared to how fast they're moving in an electric field. So what we can say is that the electric field is exerting the force on the conduction electrons in the wire, and these forces will cause the electrons to move in the wire and will create a current. The thing to remember about this, though, is the electrons aren't coming from the battery or the power supply. The electrons are already in the wire. The battery sets up, or a power supply sets up an electric field, and that's what causes the charges to flow to form a current. So it's not the battery that supplies the electrons. The battery provides the voltage, which in a sense you can think of as providing a charge pump, something that if you even want to use a water flow analogy, we can think of water flowing through a pipe as a current. We can think of a water pump as a voltage. So it's the voltage is actually what we think of as a charge pump. It gets the charges to flow through the wires, as it were, through the circuit. We can do a quick example. Suppose we have copper wire with one free conduction electron per atom. We can talk about we can calculate the drift velocity for copper wire, 12 gauge, that has a current of 10 amps. The drift velocity is about 2.23 times 10 to the 4th meters per second. That's about average for drift velocity. But that's going to be considerably less than actual current going through a circuit. We can talk about a current density as well. J is defined as a current density or a charge, or I should say current per unit area, or I divided by A. This is typically valid only if we have a uniform current density and A is perpendicular to the direction of the current. The SI units of current density are amps per square meter. And again, it's always in the direction of positive charge carriers. We're interested to establish how good a conductor is. How well does it conduct electricity? And so, for some materials, of course, the current density is directly proportional to the field. And there's a constant of proportionality called the conductivity of the conductor. And with that comes a kind of a roundabout definition, or what some people consider actually the proper definition of Ohm's law. Ohm's law states that for many materials, particularly metals, the ratio of the current density to the electric field is constant and is independent of the field that produces the current. It's what we call Ohm's law, and mathematically it's stated as the current density is equal to the conductivity times the electric field. Materials that obey Ohm's law are called, of course, ohmic materials, and of course, not all materials are ohmic. Good example of that would be light bulbs. They're not ohmic materials. Oddly enough, Ohm's law is not a fundamental law of nature, even though they call it a law. I think it's ironic that we call something like Ohm's law, which applies only in a few cases, a law whereas we call the theory of quantum electrodynamics, which is good to about 12 decimal places, we call that a theory. I guess that just goes to show you how scientific parlance sometimes evolves. Of course, that's why we always say that anytime somebody says it's only a theory, that's kind of a fallacious statement, because if it's a scientific theory, you probably can take it to the bank. In any case, let's pick up with Ohm's law next time and talk a little bit more about currents and resistance.